In this video, we are going to finish up section 3.4 on differentiability by looking at example 3.4.5 and then two theorems which relate differentiability and continuity. In this example, we're asked to show that the function f of xy, which is given here, is not differentiable at the origin. This is actually the same function that we looked at graphically in a previous example and determined exactly the same thing, that at the origin there is no appropriate tangent plane. So to show this algebraically, we need to construct the error e of xy, which is f of xy minus the expression that would be the tangent plane if it existed at the origin. So f of 0, 0 plus f sub x, 0, 0 times x minus 0 plus f sub y of 0, 0 times y minus 0. Now, f of xy we have as the function rule. F of 0, 0 we have as 0. We are missing the two partials. So let's go and calculate f sub x first of all, and we'll do that using the limit definition. So f sub x at 0, 0 is the limit as h goes to 0 of f of 0 plus h, 0, minus f of 0, 0 over h. This is the limit as h goes to 0 of, if 0 plus h is a non-zero value, we're plugging it into the function rule as given here, so we're plugging in at 0 plus h times 0 divided by the square root of 0 plus h squared plus 0 squared minus f of 0, 0, which is 0, divided by h. This is 0 times the numerator, so that whole fraction is 0 minus 0. We get here the limit as h goes to 0 of 0 over h, which is just 0. And f sub y by symmetry, right, we see that expression is entirely symmetric in x and y, so the exact same calculation with the x's and y's interchanged would give us that f sub y of 0, 0 is also equal to 0. And that is what we had argued graphically because the function value does not change along the two axes. So if we go back into the error, e of xy is xy over the square root of x squared plus y squared minus 0 plus 0 times x plus 0 times y, which means that our error is just e of xy is equal to the xy divided by the square root of x squared plus y squared. Now for differentiability, we need to examine the limits as xy goes to 0, 0, differentiability at the origin, of e of xy divided by the square root of x minus 0 plus y minus 0, both squared. Well, this becomes the limit as xy goes to 0, 0. E of xy is this function up here, so xy divided by the square root of x squared plus y squared over, and if I simplify the numerator here, I don't need to write the minus zeros, that also becomes the square root of x squared plus y squared, which is the limit as xy goes to 0, 0 of xy over those two square roots will end up by multiplying each other, and I'll get x squared plus y squared. Now, this is a limit that we looked at before. We can see that this limit does not exist by looking at the approach to 0, 0 along different paths. If we go along y equals 0, then we are going to get the limit as x goes to 0 of 0 times x, or 0 over x squared plus 0, which is just going to give 0. But along y equals x, we get the limit as x goes to 0 of x times x, which is x squared, over x squared plus x squared, which gives 1/2. So since the limit is different along two different paths, right, that's not equal, therefore the limit does not exist. And if that limit does not exist, the function f of xy is not differentiable at the origin. Now, applying the definition of differentiability every time to figure out whether a function is differentiable or not is a bit of a cumbersome task. So let's go and look at these two theorems, the second of which will tell us that there is a way that we can see differentiability a little more simply. The first theorem point, 3.4.1, is analogous to a theorem that you would have seen in your first calculus course, and that is that differentiability implies continuity. We're not going to prove either of these two theorems, but they are important results to keep in mind. This theorem says that if f of xy is differentiable at AB, then f of xy is continuous at AB. Next, theorem 3.4.2, often stated as continuous partials imply differentiability. That tells us here that if AB is in the domain of f of xy, and if f sub x, and f sub y exist in a disk around AB and are continuous. So that's what we didn't have up here. We didn't check it, but the partial derivatives that we had, they existed, but they would not have been continuous. Because if they were continuous, then f would have been differentiable. So that is a quicker way of checking. If you can calculate the partials and show that they are continuous, it is very often an easier task than doing this whole limit error calculation.